Hello everyone. In this lecture, we'll discuss how we do time scaling of the signals. So let us understand first what is the time scaling. Time scaling is basically the compression or the expansion of signal about the time axis. That means if we want to compress any signal x of t in terms of its time axis, then we do time scaling. Similarly, if we want to expand this signal, we also do time scaling. So therefore the time scaling can be of two types, which is signal expansion in time axis and signal compression in time axis. So we represent this time scaling operation of any signal. If the signal is x, then we express it with the x of alpha t, where alpha is the scaling factor. If the value of alpha is greater than 1, here it is 2. If the value of alpha is greater than 1, it indicates this scaling operation indicates the compression of xt. That means we are actually squeezing x of t in time axis. If this value alpha is less than 1, that operation indicates the time expansion of the signal. Okay, so let's visually understand this scaling operation. Here, any signal x of t is provided, where from t1 x of t is rising, then at 0 it's again decaying up to t2, then it has become 0. So this is x of t. If we want to compress this x of t, we'll use time scaling operation. Here the signal is compressed by by t by 2. That means here this is the actual signal, and we actually compressed in a way so that the signal, the time expansion, here it was from t1 to t2. Now it has become t1 by 2 to t2 by 2. That means we just minimize this time frame into half of this duration. Okay, so as long this signal is compressed from x of t, and the compression factor is 2, therefore we use x of 2t. Here 2 is greater than 1. 2 is actually representing the scaling factor, which is alpha, and the value of alpha here is 2. Therefore we just make the duration of the signal as half of the original signal. Okay, so when alpha is greater than 1, we are actually compressing the signal. What about if the value of alpha is less than 1? Here it is half. Okay, so that means x of half t. Here alpha is half. When the value of alpha is less than 1, we actually getting the expanded version of x of t. That means here the actual xt is from t1, the signal is rising, then up to t2, the signal from 0 to t2, the signal is decaying. Here when we expanded this xt, what we got, we are getting the rising signal from 2t1, and from 0 to 2t2, we actually the values are decaying. Okay, so this is the actual signal and this is the expanded version of this signal. Now you can see here if this is the duration of, from T1 to T2, it has become double of this duration. That means the signal is expanded. And for this expansion, we used, as long this expansion is, we are making the actual signal into double of its if size of its size. Therefore, we use half. If it is 1 by 3t, then we actually make this signal 3 times bigger in time axis to the original signal. Okay, so this is how actually scaling, we can visualize the scaling operation. Here, the general format of scaling operation is given, where the scale signal is alpha t, sorry, phi t, which is equals to x of alpha t. Alpha can be 1. If alpha is 1, then there is no scaling happening here. If the alpha is other than 1, it can be 0.5, which is half, 0.3, which is 1 by 0.75, which is 1 by 3. It can be 2, it can be 2.5, whatever the value. If it is if this value of alpha is greater than 1, we are actually compressing the signal. If the value of alpha, if we want to expand the signal, we'll make this value of alpha as the amount we want to expand the signal. Let's say some other examples here. This is x of t is given here, and they're about to find x of here. Uh, this is x of t. This is x of t, the graphical explanation of x of t, and this is the mathematical expansion or expression of x of t. Here x of t is expressed with 2 when t is minus 1.5 to 0, and x of t is 2 e to the power minus t by 2 when the t is 0 from 3. And other values of x of t are 0 when t is outside this frame. Okay, so let's see if we want to find x of 3t, how we'll deal with this x of 3t. Like we have done in our shifting operation, what we do when we are about to find x of 3t, we actually replace all the t's from this function with 3t, and we evaluate this function, and we'll get to it x of 3t equals to x of 3t equals to 2 when the value is 1.520. Then we'll evaluate the value of t for and we actually divide 3 by to the both of the sides. That means 1 minus 1 by 5 divided by 3 is less than equals to t is less than 0 divided by 3. If we evaluate this function in that way, what we get minus 0.5 is less than equals to t is less than 0. That means after evaluating x of 3t by replacing all the t's by 3t in the original function, we get 2 e to the power minus 3t divided by 2 and 0 for the conditions, minus 0.5 is less than equals to t is less than 0, or 0 is less than equals to t is less than 1. Okay, so this is x of 3t. If we draw x of 3t, we'll get this function where from minus 0.5 to 0 the value is 2, as mentioned here. From minus 0.5 to 0 the value is 2. You can see here from minus 0.5 to 0 the value is 2. Then again from 0 to 1 the value is is a function which is dependent to t. So to evaluate this function, we'll put t equals to 0 in this function. We'll evaluate the value, which will come up as 2. Therefore, at 0, the value is 2. And at 1, the value is 2 e to the power minus 3 into 1 divided by 2, which is a certain value by evaluating, and that can be, we assume this value is somewhere here, and we will make an exponential curve from this point to that point. So this will be our x of 3t. If we want to find out x of t by 2, we'll do the similar operation as we have done in previous practice. We'll replace all the t from this equation by t by 2. Here it was t, and we replaced this t by t by 2. Here we also replace t with t by 2, as long we want to find x of t by 2. And after evaluating these equations, these conditional equations, what we got? We got minus 3 is less than equals to t is less than 0. And for this condition, we have got 0 is less than equals to t is less than 6, and 0 otherwise. Okay, so if we draw this x of t by 2 in similar manner, we'll get this function over here. So this is how we do time scaling. Let's look at how we do time reversal. So this is the another basic time operation, time signal operation, which is time reversal. In time reversal, what we do, we actually rotate the signal into about this y-axis. That means we will if this is xt, and this is the starting point of xt, and this has come over -1, then again from 2 to 5, then again 0. This is xt. Okay, if we rotate this x of t into our its vertical axis, we will get this this function. That means the right hand side, the signal shape of right hand side will go to left hand side, and the signal shape of left hand side will go to right hand side. That means we are actually rotating this signal about this y-axis, and we have got the time reversal operation. That means the starting point has become now the ending point, and the ending point of the signal is now has become the starting point. This is how we rotate the signal, and we call it time reversal. How we do it? We just do it by using the sign x of minus t. That means if the signal is expressed with x of minus t, that means the signal has been rotated about the vertical axis, and the new time reverted signal is x of minus t. If this is xt, then the reverted signal will be expressed with x of minus t. And we can also find x of we can also determine this x of minus t by evaluating the equations. If the similar manner we have done for scaling, we have done for shifting, we can also find the time reversal signal of xt with the same way we evaluated the other scaling and shifting operations. Okay. Uh, uh, for example, this is x of t you are provided with, and you are about to find x of minus t. What we will do, you will just put x of minus t equals to 2 for minus 1.5 is less than equals to minus t is less than 0, and for this function 2 e to the power minus within the bracket minus t divided by 2 for 0 less than equals to minus t less than 3. For these minuses that you have provided here, for example, I'm let's uh, let's do a problem. For example, hold on a second. Let's we want to, this is x of t equals to, for example, 2t from 1 t is less than equals to 2, and 4 from 2 t is less than equals to, for example, 4, and 0 otherwise. Okay, if this is xt, or if we want to find x of minus t, then what we'll do, we will replace all t with minus t. Okay, 1 less than minus t less than equals to 2, 4, 2 less than minus t less than equals to 4, and 0 otherwise. Okay, so this is how we can evaluate x of minus t. To evaluate this function, what we can do, we'll make x of t equals to minus 2t, as t is multiplied with minus. Therefore, if we take this minus to the other sides, then we'll get minus 1 greater than, the sign will change, greater than t is greater than equals to minus 2. 4 minus 2 greater than t greater than equals to minus 4. Now the signal will look like x of minus t is equals to minus 2t, sorry, is equals to 4 from minus 4 is less than equals to t is less than minus 2 t from minus 2 less than equals to t is less than minus 1, and 0 otherwise. So what happened here, the signal initially x of t was from 1 to 4, and when we rotate the signal along y-axis, then we have got x of minus t, and the signal has is now from minus 4 to minus 1. That means we have just when the signal was, the actual signal was from from 1 to which is x of t. X of t was like x of t was from when it was 1 it was 2t, and 1 to 4, sorry, the signal was, hold on a second please. The actual signal was x of t. The actual signal was x of t equals to 2t from 1 is greater than t uh, uh, equals to 2 and 4 from 2 to 4, 0 otherwise. This was the signal. If we draw the signal from 1 to 2, at 1 the value is 2, at 2 the value is 2 to the 4, that means this value, and 2 to 4, this is the signal. This, sorry, this was the actual signal, and when we rotate this signal, that means when we found out the x of minus t, the signal will look like so. This is the if this is the axis, then if we rotate this signal, the signal will look like this way, and we've got x of minus t. This is x of minus t. Okay, so this is how we do time reversal operation. So that's it for today. That's it for this lecture. When in our next lecture, we'll study different classification of signal. So thank you so much for your patience listening.